A basis for a vector space is a linearly independent spanning sequence. So if you've just got some linearly independent sequence, it might not be a basis because it might not span the whole vector space. It's going to be useful to us to be able to take a linearly independent sequence and add some things in to make it into a basis. In this video, we're going to see how to do that. And what we need to help us is called the extension lemma. The extension lemma says that if you've got a linearly independent sequence and another vector which doesn't belong to the span of that sequence, then when you add that other vector in, the result is again linearly independent. We're not going to do a direct proof of this result, but what we'll do instead is prove the contrapositive. So you can see here that we've got an implies statement. We've got if this thing is true, then this thing is true. So that's A implies B. And you remember that A implies B is logically equivalent to not B implies not A. So that's the statement we're going to prove. So let's write this down. The proof is we'll prove the contrapositive which would say in this case that if the V's followed by U is linearly dependent, so LD short for linearly dependent, then U is an element of the span of the V's. So how should we do this? Well, if we know that something is linearly dependent, then we know that there is a linear combination of that sequence equal to the zero vector where not all of the coefficients were zero. That's why it's helpful to prove the contrapositive here, because saying that something is linearly dependent actually gives us something we can work with. So let's begin our proof. So since V1 up to Vn followed by U is linearly dependent, there are scalars. So let's say lambda 1 up to lambda n, which are going to be the coefficients of the V's, and then lambda, which is going to be the coefficient of the U, which are not all zero, such that I'm going to write this in summation notation. So I'm going to say lambda U plus the sum from I equals 1 up to n of lambda I Vi, and that must be equal to the zero vector in whatever vector space we're working with. So let's just call it 0 with an underline. What can we say then about lambda? Could lambda be 0? Well, if lambda was 0, then not all of the lambda i's could be 0, but we'd still have then a linear combination of the V's being equal to the zero vector. But that's impossible because we're assuming that V1 up to Vn are linearly independent. So let's write this down. It must be that lambda is not equal to 0, as otherwise we would have that the sum of lambda I Vi was equal to the zero vector with not all of the lambda i's equal to 0, and that would contradict the V's being linearly independent. Okay, we know that lambda is not 0, so what can we then do? We can rearrange. So I'm going to take this equation here, and I'm going to rearrange it to express U in terms of the V's. So I subtract the sum, move the sum to the other side, divide by lambda, which I can do because I know that lambda is not 0. So what I'll get is the sum from I equals 1 up to n of minus lambda I over lambda times Vi. Okay, that is a linear combination of v1 up to vn. Those lambda i's over lambdas are just some scalars, so we have that this is an element of the span of v1 up to vn. Okay, so we've finished our proof. We've shown that if there is a linear dependence between the vectors v1 up to vn and u, then u is an element of the span of v1 up to vn. We proved our extension lemma. So let's see why this is useful in our big result of this video, which is that if you have a finite dimensional vector space that contains a linearly independent sequence L1 up to Ln, so any linearly independent sequence, then there is a basis containing L1 up to Ln. In other words, you can extend that linearly independent sequence by adding some more stuff to make a basis. So let's have a go at the proof. So what does it mean for V to be finite dimensional? It means that there is a spanning sequence, a finite spanning sequence for V. Let's call that V1 up to Vm for V. And the way we're going to build our linearly independent sequence containing L1 up to Ln is by starting with L1 up to Ln and then adding in some of these vectors V1, V2, V3 and so on. So we're going to form a new sequence . So to start with, our new sequence will just be L1 up to Ln. And we're going to look at each of our elements of the spanning sequence, V1 up to Vm, and then some of them we'll add to this sequence and some of them we won't. So for each of V1, V2, well, let's put this slightly differently. For each I from 1 to m, we're going to do the following. So if Vi is not in the span of the sequence, then add it. So for example, if V1 was not in the span of L1 up to Ln, then we'd add it so that our new sequence was L1 up to Ln and then V1. And then otherwise, so if Vi is in the span of the sequence, we'll do nothing. So just leave the sequence as it is. Right, and I claim that the thing you end up with after you've done this procedure is a basis. Let's think about why the result is a basis. We have to show that it is linearly independent and that it is a spanning sequence. So we started off with a linearly independent sequence. We were assuming that L1 up to Ln was linearly independent. And at each step, either we did nothing, so our sequence remained linearly independent, or we added an element which was not in the span of the sequence. So then, by the extension lemma, the new sequence would be linearly independent. So it's linearly independent. The question is then, why is it a spanning sequence? Well, the final sequence has each of v1 up to vm in its span, because if we didn't add vi, then we didn't add it because it was in the span of the sequence that we had. And on the other hand, if we did add it, then certainly vi is in the span because it's actually in the sequence. So the final sequence will contain each of v1 up to vm in its span. But its span, being a subspace of v, is closed under taking linear combinations. So it contains any linear combination of v1 up to vm. So since v1 up to vm span all of v, the span of our final sequence contains any linear combination of v1 up to vm, so the span of our final sequence contains any element of v. So the span of our final sequence is all of v. So we've argued that it's linearly independent, and it's a spanning sequence, so it is a basis. And of course it does contain L1 up to Ln, because we started off with L1 up to Ln and then added some more things in. So let's see this in action. I mean, this is not just a theoretical result, it's a result that we can actually use to, given a linearly independent sequence, produce a basis containing that sequence. So the example we'll look at is the space of all width 4 row vectors. So the vector space will be this, all the 1 by 4 row vectors. And we'll begin with this linearly independent sequence L1 and L2. So you can check these are linearly independent. So L1 followed by L2 really is linearly independent, so you should check that. And V has a spanning sequence, so there's a very simple spanning sequence which is like the standard basis, only transposed. So V1 up to Vn that I've written here, and so on, is a spanning sequence for V. So we're going to use our procedure starting with L1 and L2 and using the spanning sequence V1, V2, V3, V4 to produce a basis for V containing L1 and L2. So let's remember how we did it. So initially we start off with the sequence L1 and L2. Now that's a linearly independent sequence, but it is not a basis for V. So we want to get a basis, so we should follow the procedure. That wasn't very good writing. We start with L1 and L2. So what we have to do is first of all decide, is V1 in the span of L1 and L2? Okay, we have to work this out. So we should simply see if this is possible. The span of L1 and L2 is the set of all linear combinations of L1 and L2. So all things of the form A times L1 plus B times L2. And we just want to know, is V1 in that span? So in other words, we're asking, can we write V1 as A L1 plus B L2? So what will we get when we do this? We have V1 is 1, 0, 0, 0, and that's got to be equal to A times L1 plus B times L2. So what do I have there? I've got B, A plus B, 0. So what I need then is that B is equal to 1. That's from the first entry. You can see that B must be equal to 1. And from the second entry, I get that A is equal to 0. And from the third entry, A plus B has got to be equal to 0. Okay, that looks impossible to me because the first equation says b equals 1, second equation says a equals 0. Well, 1 plus 0 is not equal to 0. So this is impossible. So v1 is not in the span of L1 and L2. So we couldn't solve those equations, so v1 was not in the span. So that means we add v1 to our sequence. So we take L1 and L2 and v1. Okay, next step. We now have to check, is S2 in the span of the sequence so far? So L1, L2, and v1. Okay, again, we have to see if we can solve some equations. And this time it turns out you can solve the equations. So the answer here is yes. And for lack of space, I'm not going to write it down. I'm not going to actually do the solution. I'm just going to tell you that, I don't know why I said S there, that meant V, of course. So V2 is equal to L1 minus L2 plus V1. So V2 is a linear combination of L2 and L1 and V1, and therefore we don't add V2. So the sequence stays the same, doesn't change. Okay, let's try the next one. Is V3 in the span of the sequence so far? So V3 was the vector 0, 0, 1, 0, and we want to know if we can make that from a linear combination of L1 and L2 and V1. And actually, I think if you look at this, you can see that you really can do this. So the answer here is yes again, because V3 is equal to L2 minus V1. That's a linear combination of L1 and L2 and V1. So 0 times L1 plus 1 times L2 plus minus 1 times V1. So we don't change the sequence again. Don't add V3. Okay, final step then. The final question is V4 in the span of L1, L2, and V1. This time you should check this. So you should try and work this out. You should write down the equations. Is it possible to write V4 as A times L1 plus B times L2 plus C times V1? The answer is no. So you'll find that the equations don't have a solution. So add V4. And that's the final step. We've gone through each of V1, V2, and V3 and V4. And therefore, the conclusion is then that L1, L2, V1, and V4, which we added because it wasn't in the span of the first three things, is a basis of our vector space V containing the linearly independent sequence we started off with.